Hi, this is Austin Hester. My final demo for IoT security is on the sensors used in autonomous vehicles. Uh, so we got our intro slide here. We can see the sensor pack and the RC car. This demo is going to be about my attempt at making a self-driving car. I'll tell you now that it was not successful. I'll go over reasons why later. Um, so part one is our midterm review. We'll go over a little bit of what we learned in the midterm review, on a short review on security of physical sensors like laser sensors and cameras. We'll go over what future steps we can do, what we've tried, what we still can do, and then we'll go over a short software design. Midterm review. In the midterm, we learned about some sensors and how they work and what they could be used for. Did some testing, and a lot of the sensors I have were easily interfered with like a TV remote even. Um, the cameras, you can point bright lights, strobe lights at them, and they kind of stop being able to recognize objects. Uh, so yeah, we'll kind of go over some of the more potentially useful sensors. So ultrasonic, that's used in like self-driving cars nowadays for like parking and lane detection, uh, obstacle detection at lower speeds, uh, and it's fairly useful for low speed, like close encounters, stuff like that. Uh, Gyro acceleration sensors. So these are actually used in a lot of things. Um, we have ring laser gyros. I don't know much about that, but that sounds really cool. That's used in like the space shuttle and like some aircraft. We have fiber optic gyros, which are in like boats, race cars. So in race cars, they're used for like the F1 car. They're used for like knowing like what kind of angle you are at and like where to apply the more power to the wheels to get like the most efficient, and like if they have like an adjustable wing, like just they provide a lot of input into like where to apply power and how to adjust to be more aerodynamic. And then we have fluid gyros as the next step of gyros, which are think like RC helicopters. Like helicopters, of course, use them, but they're probably using something more like fiber optic gyros and combination of some of these. Um, but the most common gyros we use every day are like vibration gyros. So like your phone has a vibration gyro, and it like vibrates a quartz something, and it it's good enough for most things we use. LiDAR. So this is actually a picture of like a LiDAR image. So you can see it's like pixel map rather than like a full image. Like a lot of the LiDAR stuff you'll see like fully detailed maps of like all the objects around, but it's really what is in your field of view, and it's not like a really defined picture. It's more of a pixel map, something like this. They're very expensive. Requires you to mount it on top of the car, and it spins around and it looks really silly. Like imagine like driving around like with some spinning giant thing on top of your car. It looks silly and break like if you hit like people could just like hit it, and then it would make kind of more sense for like big rig trucks, freighters. But again, rain or snow can interfere with these a lot, because the rain and snow will uh, like refract and kind of mess with the laser sensors. It would be good LiDAR even though it doesn't seem like stable enough to use like for self-driving due to like weather conditions and other things like that. It is great for like modeling floor plans, like build sites, getting a like yeah. So going into a building with a little LiDAR thing, walking around, and it just makes a model of the whole building. So that's a cool application for LiDAR. So we'll go over a little bit of the security. I'm not going to spend too much time since we went over this in the midterm, but we're just going to go over physical device security and mitigations mainly. So we have physical device manipulation, millimeter wave interference, and laser jammers. And so lasers are a sensor, they're a jammer. A laser jammer is just another laser, pretty much. So mitigations for these, so redundancy. So we have multiple versions of each sensor. We'll have a camera here, here, and here, just all around, so that if one has too much light coming in and it can't recognize obstacles, it will just kind of rely on the other one. Infrared cutoff filters, or even really whatever wavelength you're using, cut off all the other wavelengths so that you're only listening for that one. Kind of like putting on green shades and everything will turn green. Kind of like that. Photochromatic lenses, which are more commonly known as like transition lenses. I don't have them here, but like walk into the sun and they turn into sunglasses. So like shrouding cameras and sensors like with that will prevent from like really bright lights, like sunny days. It will help a lot in very sunny weather. Rain, I don't know if there's much mitigation for rain and the LiDAR. Just in the sense that the rain, we can't really stop it, and we can't really stop water refracting light. But we can reduce the receiving angle and the time it takes for us to listen, and to add randomness and intervals. So we'll go over the future steps now. So the future steps for the midterm were to assemble a prototype and write some code to control the ESC based on transmitter and sensor input, and make more money to buy more parts. So I'd like to start with some problems faced with these future steps. So first problem was some sensors are far too sensitive to like motion. A lot of the sensors I was considering I had to throw out because they just didn't prove to be useful, or like they would just have such a low range it wouldn't have been helpful. Which is another cheap and low power sensors, easy to break and interfere with. So I showed in the midterm, like it's super easy just to totally destroy one of these cheap sensors, like by, I mean, like with a TV remote. I pointed a TV remote and it was totally incapable of doing anything other than just like being stunned by that remote. And the sensors themselves attaching to the car does not have many mounting points. So I was gonna get something here, but I don't know if we can see that. I'll get some more light. One second. Let me get this light on. So I was gonna try to mount like the Pi up here in the front, and add some sensors to the bumper. And right there, I had a bumper with holes in it where I could put like cameras. But unfortunately, I crashed it, and that bumper broke. Yeah, so that brings me to the third problem was maintenance on this, and the sensors break, they fall off. There's not enough mounting points on here for something like that, and I don't have that good of mechanical skills, really. I'm mainly software. This is just something I would got to like get better at my mechanical skills, I did replace the motor with a sensored motor, which has a benefit of like faster starts, and like a sensor wire, and it can tell like which like where in the rotation the rotors are, and so that helps the ESC like apply the right amount of power to get a better start. And one of the biggest problems of them all was balancing work, life, school, everything. Just so much going on. Yeah. So I will go over a little bit more. I just kind of skipped over this part on the midterm. So the transmitter receiver, I'll go into some more detail on like how these are working. So we have here the transmitter and receiver. It's a 3-channel receiver. Channel 1 controls the servo. Channel 2 controls the electronic speed controller. 3 is aux. I'm not using it. I did try to put one of these like sensors on and was able to. It just wasn't. I couldn't get it, the Pi to communicate back to me. Like, this is another problem faced, was just trying to interface with this. It's like it seems like it's proprietary stuff, um, and trying to it uses frequency hopping, spread spectrum for code division multiple access. So these are 2.4 gigahertz receiver combo, and so the frequency hopping spread spectrum is um, we have in that 2.4 gigahertz range, we have multiple divisions. So, and each slot we send on a different frequency. So it kind of splits it up by frequency and time. And so if we, yeah, so this F5 has some markings on it. So we send our signal on the C time band, and that'll communicate with our fifth car, we'll say. I was going to go do something with this, but actually doing this and trying to hack the CDMA part of the transmitter could not find much on that, but it's worth knowing about. And then on top of the CDMA, to tell the ESC what to do, um, the receiver gets a signal and then it sends pulse width modulation pulse width modulation to the ESC to tell it what to do. ESC, servo, or the receiver gets these pulse width modulations. So I think it's something like 25% is to put on like the brakes, 50% like to go forward, 25% two in a row is to like reverse, and then 75, 100 is like steering. I'm just making those up, but I don't know the exact what they are, but it's something like that. So, and 0 would be neutral position, so just idle. So the servo, it's got a little motor in it with a big gear reduction, um, and a feedback, so it knows, like the sensored motor itself, the servo knows where in the rotation it is. So the motor can know, okay, so if I get this signal, I need to go this way more, this way, until it's full. Then it knows the motor shouldn't spin further than that, as not to like snap something. The ESC it just controls the motor. It's also controlled with pulse width modulation uh, in the brushless motor. So I kind of already talked about the sensored motor and how it knows where the rotors are. And that helps it gets better starts, and it disables that once it's at a traveling speed for energy efficiency. Oops. I may have skipped one. Okay, sorry. All right. I did skip that one. That was RPI GPIO. It's how I was using Python to interface with the Pi and control some of the sensors and read the sensors. I was really disappointed to find out that the analog sensors took a lot to set up. Um, I do have an Arduino which I could have used um, for like the gyro sensor I really wanted to use, but it was just like a lot. But I did learn a good amount of OpenCV this semester. I do want to continue playing with OpenCV. It's a really cool library. I've been using like both Python and C++ versions of it, and there's so much you can do with it. Um, it's really cool, and like both videos and images, like yeah, it's cool. And then here's the overview of the self-correction. So this is the same from the midterm, just because I kind of was unable to flesh out a prototype, um, but I was wanting to route all the signals from the transmitter receiver through the Raspberry Pi. Um, but again, there's a lot of problems faced here. So my friend actually showed me this. I was telling him about the project, and there's this thing called Comma AI, and I don't know if I trust it, but you like take your phone and you mount it on your windshield and like on your rear view, and it's supposed to like I'm not sure what exactly. It sounds kind of sketchy, but it's supposed to like be like an open source self-driving thing. Um, and and honestly, you might need more sensors than just your phone on your windshield. Um, it's worth checking out Comma AI. Uh, yeah.